We're back here again on Desmos. Last week, I introduced this idea of parametric equations or parametric curves, take your pick. These are very useful tools for describing curves where the y-coordinate is not a function of the x-coordinate. And the way that we spell these out will be different depending on what software or hardware you are using. Here, I'll be using Desmos. So I need to specify an ordered pair. The first thing in the pair is a function which governs the x coordinate. So here I'm choosing t times cosine of t. I need a comma to separate my ordered pair. The second of these things is a function which governs the y-coordinate of my curve. Here, I will choose t times sine of t. Desmos starts out, and Desmos thinks that t should be between the numbers 0 and positive 1. So I'll agree, let's start at 0. Could I go out as far as I want? No, Desmos does not like that. I really do need to be specifying a finite range for t, or a finite interval. Now, since I'm using sines and cosines, it seems fairly natural that I should have some multiple of pi here, perhaps. Let's go around, 10 times. Once around a circle is 2 times pi, so I must need to go 20 pi total. And I get this spiral. That's nice enough. Now, if I zoom out, have I gone around 20 times? Well, I can just check. Here I've gone around once, twice, 3, 4, 5, 6, 7, 8, 9, and 10. Oh, excuse me, did I say 20? I, of course, meant to say 10. Looks like I calculated that out correctly, that this would be 10 times around a circle. But a circle is not the shape I see before myself today. I see a spiral. Okay. So there'd be an example of at least graphing these things, which brings us up to date with last week's classes. We would like to turn our attention towards curves like this one, curves in which I fail the vertical line test. In fact, I've failed the horizontal line test too, so I can't describe this as x equals a function of y either. In fact, I'm pretty sure this would fail any kind of line test you'd like to put it through. Well, that is the whole point of this kind of graphing, that we can now represent curves like this. But I would like to be able to work with, all that good Calc 1 stuff. I better be able to get that far if I'd like to work on all that good Calc 2 stuff here. So what do derivatives look like for a function like this? What is a tangent line here? Well, I feel a little bit better about tangent lines than about a derivative. Tangent line, all I need to do is just literally draw a line. That one is not incredibly visible. Let's try this. There we go. There's a tangent line. Imagine it keep going in both directions. Well, I know that a tangent line has to do 2 different things. Tangent line should intersect the function at a specific point. I'll put a star on it. Then the tangent line should match the slope of the curve. And that's where I seem to be running into trouble here. Now, let's be very careful about what we mean by this point. Coordinates on this kind of a curve, well, like any other coordinate in the xy plane, they have an x coordinate and they have a y coordinate. So let's call this x and y. Very evocative names. How clever. But the different thing here is that x and y, neither of those things are independent variables. Both my x and my y are dependent variables. They depend on this parameter t here. So to choose some value of t, well, then that automatically determines my x and my y for me. I no longer have a choice once t is selected. Well, that would be half the ingredients for a tangent line. The other half of this is the slope business. Now, I'm going to be drawing on some of our expertise from Calculus 1, and I hope that you are remembering that okay. I'll try to go over what I can, but if you're having trouble with this stuff, I'm more than happy to discuss in a little bit more detail, perhaps the next time we see each other in class. Now, the thing that makes lines special as functions is that lines have the same slope no matter where you measure, no matter how large or how small you measure. I would like to know how much I move up. I would like to know how much I move horizontally. And with that information alone, I have figured out the slope of my function. We used to call these things delta y and delta x, you might remember. And I am forced here to use the hand drawing tool since I haven't memorized the keyboard wizardry to make Greek letters come out of my keyboard. Well, we know that the slope m should be equal to this quantity, this delta y divided by delta x. That's a nice idea. And in Calculus 1, we got away by saying, well, this curve is the function. Y is a function of some variable x. So this isn't just a ratio. This isn't just some fraction I cooked up out of nowhere. It's what we called the difference quotient. That was our whole business for f of x plus h minus f of x divided by h. You remember that? Well, that's not going to work here. At least, not exactly. So I need to clean up some of these drawings so I can get a better look at this picture. There we are. Let's zoom in a bit before I go any further. So hereabouts is the coordinate I want. And like many other things, this curve, when I zoom in, appears almost to be a straight line. Almost. Well, what I should be able to do here, there's that same point that I care so much about. At this zoom, this magnification, I should be able to find my delta y, my delta x, by saying that I've got the coordinate that I want. It's a little star. And I've got some other coordinate that is very, very close to it. Here is a heart. And what we're going to do is we're going to take the coordinates for both of these coordinates, star and heart. So star has coordinates x of t, y of t. Heart has coordinates that are slightly different, but they still follow the same general formula. That the coordinates for heart should be x of, well, it's the same function, x, but it's a slightly different input. T prime, let's call it. So prime here just to mean that it's different from the t. Maybe t star, that we don't get confused with the derivative. We're not doing a derivative just yet. Similarly, the y function is the same, but the t coordinate is different. So these would be my two different coordinates. Well, what is the difference in the y's here? That's literally what I mean by my delta y, the difference. Delta is the Greek equivalent of d, d for difference. Delta y is going to be just literally the difference, subtraction. So y of, let's say, t star minus y of t. And similarly, x, what's happening there? Well, I would want to calculate the function x at t star minus the function x evaluated at t. What is the difference of my two x coordinates? And I would call this I would call the result of this subtraction delta x. Very well. So this should approximate the slope that I want. What am I going to do? I'm going to divide these things. Delta y divided by delta x, because of course I want rise divided by run. But this is only an approximation. What I would like is the actual value for this slope, for this instantaneous rate of change. So what else am I going to do? I will take the limit, and here I will take the limit as t star goes to t. That's a nice idea and all. And as long as I have a curve that is smooth enough here, this should all work. But what is this calculation really? Well, what would it mean to have two different values of t, one very close to the other? Well, I already talked about this h business with my difference quotient. Maybe when I'm close, what I really mean is t plus h. And h is some very small number. Well, that would change the way that I write this limit. I really want the limit as h goes to 0. Not bad, not bad. Let me play around with this some more. If I can get this limit to look like derivatives, then everything that I know about derivatives will work here. Does that make sense? We know how to handle certain limits of difference quotients. So please remember that we have that name for a special kind of formula, and here it is occurring again. If I can rewrite this formula to look like perhaps one difference quotient, perhaps two of them, then just like that, everything that I know about calculus 1 is back on the table. I'll just need to tweak it a little bit to keep it working in this new context. Well, I've got a fraction. I've got a quotient, if you want to be fancy about it. Numerator says, numerator says change in y. So let me call this y of t plus h minus y of t. That's my numerator. I'll turn off the graph for right now. I'm really more using this as a whiteboard. Denominator is going to be the difference in those x coordinates, x of t plus h minus x of t. Okay. Well, I've got some differences and I've got some quotients, but that's not really what I meant until I have h's on my denominator. Well, I would like an h to be dividing both of these things that I see, both of these differences. And I know that as long as I perform the same operation on the numerator and the denominator, then really I haven't changed this formula. Okay, I've rewritten it slightly, but the result of the calculation is the same. There's only ever two tricks in mathematics. One of them is multiplying by 1. The other of them is adding by 0. It's just a matter of choosing the right 1 or the right 0 for what you're working at. So when I multiply this through, I'll get a denominator of h over here, and I'll get a denominator of h over here. That's not so bad. Well, there are my two difference quotients. Maybe this one up on top I'll label blue, and this one on bottom I'll label green. But I know how difference quotients work. As long as x and y are functions that do have derivatives, then the numerator here is the derivative of y. The denominator is the derivative of x. So I'll call these things y prime and x prime. So again, in this context, both x and y are functions of this other parameter t. And now I have a formula that I am very well practiced at calculating. I know how I can find derivatives of various formulas. And now it turns out that the slope of a parametric curve is determined by calculating two derivatives, dividing one by the other. So let me test this idea, again using this curve that I care so much about. Here it is. So I'm going to pick a certain value of t Now, I'm already using t here to parameterize this curve. So I'm going to pick a number, let's say a equals 5. That's just some number. Which point on the curve is it? If a equals 5, have I even gone a single time around before cosine and sine loop back on themselves? Well, I can just check by asking Desmos, where is the coordinate a times cosine of a, comma, a times sine of a, like so. And Desmos lights it up in purple. So no, I've only gone 3/4 the way around and change, but there is my point. The nice thing about this setup is I can then move the slider around to move the point. That's pretty cool. Now, the slope of the tangent line needs 2 things. I have here 1 thing. I have the point that I want. What I need, in addition to this, is the slope of the curve. So to that end, I need derivatives for both of my x and my y functions. Well, that's not so bad. A little bit of product rule never hurt anybody. It looks as though my x prime of t, well, take the derivative of t times cosine of t. I'll get cosine of t plus t times, negative sine of t. Let's just call that subtraction. Looking good. And likewise, for my y prime of t, I'll have sine of t, and I'll add to this t times the derivative of sine, which is the cosine of t. There we are. And to fill out my derivative here, to fill out my tangent line here, I will use point slope form because that's the one that I like the best. That's just me. I'll have y minus the y coordinate that I'm trying to hit, the one in purple right here. So for me, a times sine of a. This quantity needs to be equal to the slope of the curve. Again, not the function, because this thing isn't a function. So my slope is y prime divided by x prime. Sine of a plus a sine of a, that's the numerator. And I can highlight this all, hit the slash sign to get a fraction very quickly. Denominator cosine of a minus a sine of a. So this is specified for the particular coordinate that I want. And then multiplied by x minus the x coordinate that I want. Here, that is a times cosine of a. Now, it doesn't look quite right. I've at least hit the point that I want, but something seems to have gone wrong with my slope. What is it? Do you see it? So this slope seems to be off somehow. I've got y minus a particular value of y. I've got my x minus a particular value of x. Numerator should be y prime evaluated at the t coordinate that I want. Derivative of my y function is sine of t plus t times cosine of t. That's looking all right for now. Aha, of course, I have mistakenly put in sine where I should have put in cosine. That fixes everything. So, as long as you're diligent about putting these formulas in your calculator correctly, we get exactly the tangent line that I'm looking for. Now, the cool thing about this is that everything in this tangent line formula is completely determined by the specific value that I chose for t. T controls everything on parametric equations. It controls the point that I'm looking at. It controls the value of my two derivatives, my x prime and my y prime. And so t actually controls all of the information that is relevant in building up this tangent line. And of course, because it's Desmos and because I can animate these things, I can have the purple point move around this spiral all the way along, dragging this tangent line. Maybe a little bit slower than that. There we are. So here is a neat little trick we can do just to show off that, yes, I've still got tangent lines, I've still got derivatives, looking slightly different in this context than what we've done before, but producing very similar results, and again, very similar applications. Let me pause this for a bit. If I am close to this coordinate in purple, and I wish to approximate this function, then the tangent line at least does a decent job while I'm nearby. Perhaps there's more advanced tricks I could use. We only got to Taylor series by saying we've got lots of information to work with. The derivative, the second derivative, the third derivative, and so on. Now this video is getting a little bit deep than I really intend for a single viewing. You might want to rewind and watch some of this stuff a second time. I'll return to this idea of the second derivative in a following video. Rest assured, we're not going to be doing Taylor series in this situation, but in theory, maybe you could. We'll save this for upcoming